Welcome back, ladies and gentlemen. This will be quick. We're going to talk about circular velocity. Now, you guys already have the notes on it, and the notes talk about it in great detail, but here's kind of the key thing. It's velocity. That's it. That's the key thing. I know, right? Really shocking. So if it's velocity, what does that mean? Well, what is velocity? What's the equation for velocity? What's the definition of velocity? If I asked you guys to write down the velocity equation or its definition, what would you write? I really hope that you wrote something like this. Because that is the velocity equation. Great. But we're dealing with a circle. So, what's time for a circle? We just did a video lesson about this. Time for a circle is, of course, period or frequency. So I could rewrite this equation as velocity equals delta d over period or delta d over frequency. Right? And that means the same thing. That's the time of a circle, and that's what we're dealing with, circle. So the only thing left is, what's the displacement? What's the displacement around a circle? Well, there's the hint. Around a circle. Around a circle. What is the formula to describe the position of an object around a circle? You learned it in grade 7. I know. Remembering things I was taught previously, that sounds like work. Delta D for a circle is the circumference, 2 pi r. So I put this with that, and what I get is that the motion, the circular motion, the circular velocity, I should say, is 2 pi r over period, or 2 pi r over nu. That's it. We're done. What, you wanted something harder? All right, fine. Hold on. Look, here's the point. It's a circle, right? The fact that it's moving in a circle means that certain things are defined by its circleness. The circumference of the circle is that outer displacement, right? It's not like I'm going through the middle. I'm going around, and I know what that around shape is. It's a circle. That's always the key. It's a circle. And I know what the time is because we just worked that out. It's either period or it is frequency. And that's it. Just because it's a circle doesn't change what velocity is. Velocity remains identical. It's still the displacement divided by the time. But for a circle, the displacement is, of course, circumference. And the time is going to be period or frequency. And that's it. That's the whole idea. Now, there is one tricky part. It's a circle, as you have heard me say about 1 billion times so far. So if I am going around the circle, what is the direction of my motion? That's tricky, right? Like here, I'm going up. Here, I'm going right. Well, your left. Here, I'm going down. I can't describe the direction of motion with linear directions, left, right, up, down, because it's not a linear, it's a circle. So instead I describe it with clockwise or counterclockwise. I did those backwards for you guys. It would be clockwise for you guys and counterclockwise. There we go. Okay, that makes sense. So the position, the displacement, is not going to be a single direction. It's going to be a ever-changing circular direction, either clockwise, meaning going with the clock, or going against the clock, counterclockwise. What's the velocity? Well, we said earlier that the object is going to move in with constant speed, but of course constant speed is not the same as constant velocity. What's the difference between speed and velocity, you might remember? Well, speed is the distance divided by time, and velocity is the displacement divided by time, and displacement has a direction because it's a vector. So, what's going to happen? Well, think about it. Up here, I'm going this way. Here, I'm going this way. Down here, I'm going like this. And over here, I'm going this way. At each of those moments, I am moving in a particular direction. And that direction is like this. Right? I'm going to go like this. And then here I'm going that way. Here I'm going that way, sort of down. Here I'm going to go up, right? And you'll notice that the marker stays in exactly the same orientation the entire way around the circle. We call that, right? Instead of using a marker, what if I used a ruler? This has a name. It's a line that touches another line at only one spot. What do we call a line that touches another line at only one spot? We talked about that back in graphing a long time ago. Tangent. Yeah, tangent. Some of you remember, I hope. So here's the big thing that's different. It's a circle, which means that the object that is going in a circle will move in a circle. So an object that I spin in a circle will move in a circular manner. So it will go here and it will go around, following the circumference of that circle. The velocity of that object will be a line tangent to the circle, a straight line that goes directly like so. Now, usually I will do a demonstration in class, and I will take this very hoop, and I will take a ball, and I will place this hoop against a flat surface like so. Except that I will put it down, because that's important. And I will take the ball, and I will set the ball to spinning around and around and around, and then I will lift up the hoop, removing the boundary that is keeping the object moving in a circle. And what inevitably happens the moment you do that is that the object will follow Newton's laws and continue to move in a straight line. What do I mean by that? I start here and I'm going up, and as we see as I go around the circle, that marker continues to point, basically we could call it forward. It's pointing in a direction that is tangent to the circle. Well, if I let go of the circle here, if I remove the circle, boom! This thing doesn't keep going like this. No, because it can't. It just goes straight. It'll just continue on, just like this, all the way through space. Now, the video that I have recorded, there's a secondary video here, not that I've done, but one that is listed in the plan, and that one will give some examples and show some diagrams about this. So I do recommend you take a look at that. I always use this. That particular video is only good for the first 10 minutes or so. The rest of it's a little too advanced for us. But it's good, so I recommend that. Now again, I can't unfortunately do that demonstration very easily. I'll see if I can't find a way to splice that in maybe, but in the meantime, just think about it, right? The marker is continuing to follow this path. Well, if I take away the circle, if I remove the thing that's keeping it in the circle, it will just continue in a straight line, because that's how Newton's laws work. An object in motion stays in motion unless acted upon by an outside force. Yeah, that's right. Forces are involved in circles. I know. Shock, right? Okay. All right. The examples are pretty trivial, but let's do one of them. Get it out of the way. Work with our new and exciting equation. So it says here, a model airplane moving counterclockwise in a circle. So we've got a model airplane. Okay, here we go. It's going to be moving counterclockwise, so we'll make a little airplane. There it is. And we'll give it a little fin. And I guess we'll put a little star on the wing. And it's going to go counterclockwise in a circle like this. Okay, and it says here, let's see, where was it here? A radius of 10 meters. And it says it's got a 30 RPM. RPM means revolutions per minute, which is another way to say cycles over 60 seconds. Okay, and we're going to have a series of things that I'm going to ask you guys to find. Okay, step one. What's the period? Period. Which one's period? Oh, can we remember? It's, yes. Seconds over cycles. Okay, so it says that I get 30 revolutions per minute. So that's going to be 30 cycles in a minute, which is the same as 60 seconds. So that's going to be 2 seconds per cycle. It's a pretty slow model airplane. Frequency. Frequency is easy. I mean, I could do the math. There's actually a button on your calculator to do it for you. Depending on which calculator you have, of course. In the case of this one, it's right here. It's the 1 over x button. There might also be on your calculator. It's either going to be 1 over x, or it's going to be x to the minus 1, either one. And what you do is you put 2, and then you push that button, and it gives you what the answer is, 0.5. It's called the reciprocal button. And what it does is it basically does the math for you of flipping this. Instead of putting it as 60 over 30, it puts it as 30 over 60. It flips it. It's called the reciprocal. It's the name in math. So we'll just write it down just to make sure we've got all the notes down here. So it's cycles per seconds. Okay, C. What's the circumference? Okay, circumference, we know how to do that. It's 2 pi r. You guys learned that in what, grade 7? Yeah, grade 7. Good time, grade 7. Probably. So 2 times 3.14, you're going to want to use the pi button on your calculator, times the radius, which in this case is 10. So I go 2 times pi, where's pi on the calculator? It is, times 10. 62.83 meters. And then the last one, D. What is the velocity? Well, velocity is just circumference over period. Circumference is going to be, as we just discovered, 62.83 over period, which we said was 2. So 62.83 divided by 2 is equal to 31.4 meters per second. That's it, we're done. Honestly, guys, this type of questions are very comparable to the stuff you guys did in grade 10. The only difference is, drum roll, it's a circle. That's the only difference. It's all a circle. Small correction. Yes, because we could use circumference over period, but we could also do velocity is equal to 2 pi r nu. Yeah, slight mistake there. I just noticed in my previous description. But because period is equal to 1 over nu, right? That's what the reciprocal button is for. That means that it would be like this instead of having it on the bottom. That's a small thing. Anyway, there you go. Pretty straightforward. And to be honest, I mean, I'm just gonna breeze it. I'm just gonna breeze it right here. Acceleration. You ready? Boom. Here it is. Remember, acceleration. Acceleration is equal to delta v over delta t. Well, look, we know what v is. We know what t is. We can solve this. It's very easy. We plug it in. We'd have to do a little bit of vector algebra, right? Because this number here is v, not delta v, so we'd have to find delta v. And to be honest, it explains it in the notes. It's step by step by step. I want to go outside. I'm going to go outside. So you know what? I'm going to tell you really quick. We're going to do it simple. We're going to do it quick. If you've got questions, check the notes and or ask me. Don't worry, I will show you how. But this is the key thing. It boils down to this. The acceleration of a circular object is equal to velocity squared over r. Basically, we spend a whole bunch of time doing a whole bunch of math, and we prove it down to a single simple equation. Boom, done. That's it. Whatever the constant velocity is, you write that in. Heck, you can even use this equation and plug it in directly. Right? So for here, this whole thing here, we got this was 31.4. Okay? Let's find the acceleration. Boom, we're doing E here. E, acceleration equals who knows what. About to figure it out right now. What do? I take 31.4 divided by 10. Acceleration is equal to 3.14 meters per second squared. Done. That's all I have to do. Because again, it's a circle. And this is the thing that I want to stress here. It is a circle. So it does circle things. Which means all circles behave the same. The displacement of a circle, he tries. The displacement of a circle is the circumference. There it is in green. The velocity of a circle is tangent. There it is in blue. And the acceleration of a circle points to the center. Why? Because it's a circle. Why is it so different? Because it's a circle. And previously we talked about lines. Why does it point to the middle? Well, think about it, right? As I'm starting off with my velocity, it's going this way, and then it has to go this way. Now, this is part of that calculation that I kind of skimmed over because I didn't want to do it right now, that talked about how to get this. But what we see is to go from here to here, the only way to do that is if I have an acceleration that points like this during the whole time, in, towards the middle. And that's kind of it. Broadly speaking, if you just remember that the displacement is around the circle, the velocity is tangent to the circle, and the acceleration points to the center of the circle, you're kind of done. I know, it's very straightforward. It seems almost too easy. It just kind of is. The only reason it seems easy is because you guys have already been doing so much of this stuff. A lot of this stuff has become second nature to you, and that's good. I'm really pleased that you guys have managed to tackle this for so long. It's hard to keep this motivated throughout the entire year, let alone when you're stuck at home and they have much more interesting things to do. But here you are. It's a circle is the answer. It's a circle. That's why green is a circle, and that's why blue is a line, it's a tangent, and red seeks the center. With that, ladies and gentlemen, I'm going to leave you for the moment. You guys have most of the information you need in order to solve everything. I mean, I guess, much as the notes say in the next bit, I could mention this. There is a force. Force is equal to mass times acceleration. Acceleration in this case is v squared over r. Mass is whatever the mass is. There you go. There's your force of a circle. I know. At this point, we're just throwing things together, and there's the answer. Boom, done. Take a look at the notes, read through them a little bit, ask questions if you're getting a little bit stuck, but that's kind of it. The booklet in this particular unit it's broken up into sections, types of unit questions. I will make a video talking about forces in a little more detail, probably Thursday. I just want to give it a little time. But for those who are kind of working ahead or ready to go, it's all in the notes explained in great detail. And I will leave that to you guys. The question booklet, I think, has 48 questions, and I believe when I talked to Mr. Collinville about that, he said that's 40 more questions than they need to understand this stuff. You guys are going to be fine. If you've gotten this far, you're kind of already through the hard part. Okay? So I will talk to you guys later.